Toward the end of our last class, I'd gotten a little bit into section 6. And the idea of that is that you can find the electric field due to some distributed charge by thinking of that charge as being a collection of little point-like charges, and using the superposition principle, add them up. If it's a continuously distributed charge, then you divide it up and take the limit of infinitely many infinitely small pieces. And when you sum it up, that's an integral. So I'd gotten through all but the mathematical cleaning up. For the first example here, we've got a rod lying along the x-axis, and maybe I should summarize some of what's already in your notes, just to kind of get you back into it. So, hold on. As is already in your notes, the field of one typical little piece was Coulomb's law constant. The basic formula here goes back to pretty much the beginning of the course. The field of a point-like charge equals the Coulomb's law constant times q over r squared. And then you stick a unit vector on there to give it a direction. Okay? In this case, since we're assuming the rod to be positive, that's what you always do in these general problems where you don't have any specific numbers. Since we're assuming the rod to be positive, the field points away from the rod, which would be toward the left. The charge on one typical little piece of the rod is found from the charge per unit length. The question says that the charge is uniformly distributed. That means charge per unit length for the entire rod equals charge per unit length for the infinitesimal piece of it, and that allows you to set up a proportion that tells you dq equals the thing in parentheses. And then you could call this r squared. I called it x squared because the rod lies along the x-axis. The notation doesn't really matter. So somewhere around here is where I left off. The field of the entire rod equals the summation of the fields coming from its many, many pieces. So you integrate, an integral is just a type of summation after all. You integrate from the one end of the rod, which lies at x equals d, to the other end of the rod, which lies at x equals d plus L, and dE is that thing up there. Well, in this expression I wrote here, everything aside from x is a constant. Q is the total charge on the entire rod, that's just a number. L is the length of the rod, that's just a number. The Coulomb's law constant is a constant, that's why they call it the Coulomb's law constant. So all of that stuff can be written out in front of the integral, kind of getting it out of the way like this. And then you integrate. Hopefully you are aware that the integral of x to the minus 2 dx is x to the minus 1 over minus 1. But if you are a little shaky on that, I should remind you that there is a short table of integrals in your reference handout where you might be a little shakier, as it's like, I have to integrate the cosine. Is that sine or is that negative sine? Well, you can look that up. Let's see, this minus sign gets canceled by that minus sign. And we have, I don't feel like writing all of that again. The squiggle stands for all of that. The important thing is we've got 1 over d plus L minus 1 over d. Evaluate at the upper and lower limits of integration. And I suppose you could call that the answer, but one thing I distinctly remember from when I was taking calculus several years ago is that after you finish integrating the thing and you look in the back of the textbook to see if you got it right, it never looks like the thing on the piece of paper in front of you because they played with it some to make it more simplified or just prettier or something like that. So with the same sort of thing in mind, before I mean, you know, if you get this far, you're in pretty good shape as far as I'm concerned, but I'm going to find a common denominator and combine those two terms just because I think it looks better that way, and probably other people would too. So we've got the same coefficient there that I don't feel like writing out in detail. And the common denominator with those two fractions would be d times d plus L. So stick on a factor of d over d here, and d plus L over d plus L there. And then when you subtract, d minus d cancels out. And shifting things around a little bit more, and then I'll call it the answer. You've got the Coulomb's law constant times Q over D times D plus L. Points in the negative I direction, points to the left. One way of checking yourself when you're doing something real and don't have an answer in the back of the book to look at is stop and think about the extreme cases, the limiting cases. What if somebody was really, really far from this rod? Like if the rod was an inch long and you were standing 50 feet from it, what should the electric field be? Well, at that distance, it looks like a point charge. So this should reduce down to the Coulomb's law expression. And sure enough, if L is like 1 inch out of 50 feet, it's practically zero. If you just drop the L, it becomes Q over D squared, Q over R squared, if you'd rather say it that way. And so that sounds like it ought to be right. Another example. Basically, all there is to section 6 is I go through a bunch of examples, and then I have one at the end for you to work on, and they're all examples of the same thing. And then we go on to section 7, which has more stuff packed into it than this, but people seem to need the time to digest this. So number 1 here was a one-dimensional example. Everything happens on the x-axis. Next one is two-dimensional, where you need a full vector treatment. In this one, the distance, x or r if you prefer, was the variable. Theta was constant. In the next one, it's the other way around. R is constant. Every piece of the rod is the same distance from the point where you're finding the field. It's theta that changes as you work your way from one end of the rod to the other. So this is very similar to, I'm pretty sure there's a problem in the homework where it asks for the field of a charged semicircle. Well, I just changed that a little bit to make it into this here. Instead of half of a circle, it's a quarter of a circle. Do little details like that. Uniformly charged, just like we had in number 1. So once again, step 1, divide the rod into point-like pieces and write down the field of one piece. And some sort of a diagram is probably a good thing to do as part of that. So here's this curved rod, drawn much thicker than it actually is. It's supposed to be just a thin thing. And right there is a typical little piece of it. Just like before, we're assuming the rod to be positive, so the field of that little piece would point away from it. This DE vector makes an angle theta with the x-axis. And as you work your way from one end of the rod to the other, theta is going to change. The limits of integration here are going to be from, I think we start with, negative pi over 4, 45 degrees if you prefer. Negative pi over 4 to positive pi over 4. So theta will be changing as we go along. The electric field vector is a vector. It says just above the question. Remember to treat this vector as a vector. In other words, it's probably best to look at it in component form. If the length of that hypotenuse is DE, then the y component is dE times the sine of theta. And the x component is dE times the cosine of theta. A few other things to label on here. The little dotted lines I drew there, not quite as straight as I would have really liked, they go from one end of my sloppily drawn little piece there, from one end of it to the origin, and the other line goes from the other end of it to the origin. And that's theta, vertical angles with this one over here. So theta, theta. That little bitty angle between the two dotted lines, that's d theta, meaning how much theta changes as you go from one end of this small piece to the other end of that small piece. R is the distance from the origin to this piece. That'll be the same for every piece on the rod, because the point where we're finding the field is at the center of the semicircle. And the length of my little piece, everybody read that down low like that? It's not like behind the computer screen or anything. That's R times d theta. Where that comes from, somewhere around the middle of physics 131. When I first started going over rotation in physics 131, I said, what if you've got a wheel, for example, and that wheel has a radius r, and the wheel turns through an angle theta. S is the arc length. Point on the edge of the wheel moves a distance s. Well, I said back then that s is equal to r times theta. Meters equals meters times radians as far as the units go. That's what I've done here, except instead of some finite angle theta, it's this vanishingly small angle d theta. In order to calculate this vanishingly small length, r times d theta, the length of my little piece there. So that's the setup. There's my little piece of the rod. There is its field. And as it says further up the page, the field of that one little piece, dE, equals the magnitude of the field is the same expression from section 1 that I used in the previous problem, that I'm pretty sure will probably get used in the next problem too. Coulomb's law constant times Q over R squared. So we'll have to make some substitutions into that before we're done, but for starters, Coulomb's law constant times the charge of the little piece over R squared, where R is its distance from the point where you want to know the field. That's the magnitude of the field. As it says further up the page, for any kind of a vector, whether you're talking about electric fields or a momentum vector or anything else, You can express it as its magnitude times a unit vector. And in this case, that unit vector left my camera behind. So that part of it is dE without an arrow over the top. The magnitude of the field the magnitude times the direction gives you the entire vector, or the direction is described with a unit vector. Now, maybe you associate the basis vectors I, J, and K with the name unit vector, because that's what a unit vector is usually meant until now. But what a unit vector actually means is a vector whose length is 1 unit. Doesn't necessarily have to point along one of the coordinate axes to be a unit vector. Put the components of this into the Pythagorean theorem and think about what its magnitude would be, okay? The magnitude of a vector is square root of its x component squared plus its y component squared, Pythagorean theorem. Square root of cosine squared plus sine squared, that's one of the trig identities from when I went to school, it was 11th grade math. That's equal to 1. So anyhow, a unit vector to give it a direction, or if you just look at it this way, here dE times a cosine of theta. Shift this back over. dE times a cosine of theta is the x component. dE times the sine of theta is the y component. So that is the field of a piece. So step 1, divide it into point-like pieces, write down the field of one piece. Step 2, use the charge density to substitute for dq. Okay. Similar to the way I did number 1. Just like before, I'm using a capital Q to stand for the charge of the entire rod. It says that in the question. The length of the entire rod, the question says it's a quarter of a circle. The circumference of a circle is 2 pi r. If this is a quarter of a circle, its length is a quarter of that, which would be 1/2 of pi times r. Because it's uniformly charged, the charge per unit length for the entire rod is the same ratio as the charge per unit length of a typical little piece of it, like that one. So length of the rod is that. I explained earlier that the length of the little piece is r d theta. The r's cancel each other out, which simplifies things down a little bit. So when you solve it for dq, that's what I can put in my expression for dE as a substitution for the charge of the piece. This is now in a form that can be integrated because everything is either a constant like Q or pi, or R is a constant this time because our charged wire here or thread or whatever it is, it's been in the shaped part of a circle. Every point on it's the same distance from the origin. So these are all constants. Everything is a constant or it's a theta. Okay, you have to have everything. If you're just doing a regular single integral, you have to have just one variable in it in order for it to be integrable. Next step, other substitutions if necessary. Yeah, that's not necessary in this case. So we can skip over step 3. Final step, integrate. Add up fields of all the little pieces. The limits of integration, once again, are negative pi over 4 to plus pi over 4, because you go from one end of the rod to the other end of the rod, adding up contributions of all the little pieces as you go along. Now, if you are alert, you can save yourself a little bit of time and effort at this point without actually going through the details of performing the integral. Maybe you can see that the y component is 0. Because of the symmetry of the situation. Okay, let me draw a little sketch under there. There's my curved rod again. There's the x-axis. For every piece up here, which produces an electric field that points right and down, there's a corresponding piece, same distance below the axis, that produces an electric field that points to the right and up. So the y component of that one points up, the y component of that one points down. The x components are going to add up to something, but the fields from the y components cancel in pairs as you kind of work your way out from the center toward either end. And so without bothering to crunch through the math, you can argue that term away because of the symmetry of the situation. I'm almost done. So we have just the x component. That pi combines with that pi, and the 2 cancels with the 4. It's going to be 2 pi squared epsilon naught q over r squared the integral of cosine is the sine. Cosine of 45 degrees is the square root of 2 over 2. Cosine of negative 45 degrees is negative square root of 2 over 2. Put them together, and the whole integral is equal to the square root of 2. And so here's the answer. Sure I copied that right. Yeah, that looks good. And if you feel like looking on through the rest of this before our next class, that wouldn't hurt you any, although it's not required.